So this will be my first time doing any sort of like mini recorded lecture or type of thing. So bear with me, it's my first time, so it may not be the best. I'll probably get better as we go throughout the semester because I'll probably continue doing these because I think they'll probably be a little bit of fun and they'll be good practice for me and it's beneficial to you guys. So hybridization essentially deals with the problem that carbon here, as you can see, carbon has 4 bonds to hydrogen, and these are all of equal length. We already know this from Gen Chem. All of these have equal distance between the 4 bonds. That's something that we've discussed, and we don't need to go into that right now. But essentially, how can carbon have 4 equal distance bonds and equal bonds of the same amount of energy if there are 2 electrons in the 2s and 2 electrons in the 2p orbitals? We know that 2s are lower in energy than 2p. So how can all of these bonds be the same amount of energy between carbon and hydrogen? Well, that's answered through hybridization. So with a carbon that has 4 sigma bonds to hydrogens, we know that it is an sp3 configuration. Now what that means is these 2 electrons in the s orbital and the 2 electrons in the p orbital, they hybridize the p orbitals with the s orbital to form 4 equivalent sp orbitals. sp3 orbitals specifically, because there's 3 p orbitals contributing and 1 s orbital that contributes to it. And so these are all of equal energy, and they all contain 1 electron. And then obviously you still have your 1s. That is unchanged because that is a core electron shell. And so we have this idea of sp3 orbitals, and now we have 4 different orbitals that contain 1 electron, and they're all of equal energy levels. So these are our 4 orbitals that contribute to being able to have equal bonds between carbon and hydrogens at equal distances, because now all of the orbitals are on the same energy level. As opposed to when we had 2s and 2p, we had 2 higher energy and 2 lower energy. I'll explain more when we get into sp2 and sp3 about shape, but essentially we have a newer type of representation of molecular shape and 3D shape for carbon specifically, with these dashes and wedges. So essentially, a straight line, a normal line, is just, it's establishing that they're all in the same plane. So if you imagine you held your hand out and you held your pointer finger and your thumb out, kind of like a finger gun, those two are in the same plane because the tip of your fingers essentially are in line with each other. Versus if you took your finger gun and turned it towards your screen, now you have one tip of your finger coming towards you and one tip of your finger going away from you. That's essentially what the wedges and dashes are explaining. They're explaining that you have not everything all in one plane. You have some coming out towards you, like in the case of this hydrogen here, and some going away from you, in the case of this hydrogen here. So then when you get towards sp2, now we have the idea of sp2 hybridization. So with sp2 hybridization, you have this, now you have a double bond here. And this double bond is special because double bonds are made out of 1 sigma bond, that's really hard to draw with this, and 1 pi bond, which is this second one here. And what's great about having pi bonds is pi bonds are only formed one way, and it's between 2 p orbitals. So when you have 2 p orbitals that are side by side, meaning the sides of these dumbbells are the ones that are going to be overlapping and interacting, these sides are what make up the p orbital in this area here. This makes up that pi bond right there. So that's essentially how pi bonds are formed. And this can be any of the three versions of pi bonds. It could be the y-axis pi bond or p orbitals. It could be the x-axis p orbitals or the z-axis p orbitals. It doesn't really matter. It's just side by side p orbitals are what create a pi bond. So we know that we have two p orbitals or one p orbital from either atom that is going to be involved in this bond that's right here, this double bond. But we also know that we now have 3 sigma bonds between carbon and another atom. Over here it's unknown what it's bound to, and here we have 2 hydrogens. So we know that there are now 3 sigma bonds that are of equal energy, because the only thing different is this pi bond, which we have established is p to p orbitals. So sigma bonds of equal energy means that we're going to be having 3 hybridized orbitals with 1 electron in each of them. And then we're going to be having that 1 p orbital. And so these 3 that we formed are sp2 hybrid orbitals. And then, of course, we still have our 1 s orbital. And so this creates the situation where we have 3 equal sigma bonds that create this hydrogen, carbon, and carbon to whatever molecule, and then the pi bond, which creates the second in this double bond. Now, if we were to add a third bond to that carbon, so let's make this CH. So this is 1 sigma bond here. And then we have carbon triple bonded to some other element. Now we have 1 sigma bond here, 1 sigma bond here, and then we have 2 pi bonds. So now we have 2 of these p orbital overlaps to form 2 pi bonds. So that means we have to have 2 p orbitals remaining with electrons in it to have this overlap when we have a triple bond. And then we also have the formation of 2 hybrid sp orbitals with 1 electron in them. And then, of course, our 1s, because that is a core electron shell and will not change. So this is how we're able to make this sigma bond and this sigma bond equal in their energy. And then these 2 p orbitals, they are equal in their own energies because they're both p orbitals and they're degenerate, meaning they're all having the same energy level. And those form our 2 pi bonds when we have a triple bond. I hope that was able to clear some things up for you guys, and let me know if you have any questions.